Right, well, this talk is about determining natural durability in Australia, and I'll also touch on some work that we did on vineyard posts and also looking at natural durability relating to tree age. Where are we? I should have looked at this earlier. This slide shows the main sections in a eucalypt log dealing with important for natural durability. So the sapwood band is non-durable, but it's usually treatable with wood preservatives. The majority there is outer heartwood, which is where the most durable part of the timber is located. And durability in eucalypts is mainly due to polyphenols or tannins. And then the inner heartwood is usually less durable part of the timber. And that's because it's a combination of juvenile heartwood, which is usually not as durable as mature heartwood, and also simply tree age, where with time some of the polyphenols degrade or polymerise to become less durable. So you can see a little bit of decay already starting in that inner heartwood there. Before 2003, all the information on natural durability was spread across several standards in Australia. So the main wood preservation standard, 1604, had some Lichtes sapwood resistance information there, and also in-ground durability. Whereas the termite standard had a list of termite-resistant timbers in there, and there was also a pole standard with in-ground durability ratings as well, but sometimes they went out of sync with the 1604 standard. So in 2003, these were all brought together in the 15604 standard, and the later version has you can see the information there. So Lichtes susceptibility for the sapwood of hardwoods, and then termite resistance for basically for house framing. So what we call hazard class 2, indoors above ground termite resistance. Then the next two are in-ground durability and above-ground durability outside, and they're mainly determined by decay, although termites are also important, but they're mainly decay durabilities. And then the last one is Marinebora resistance, which was a new column that was added in 2005. The main natural durability trial set up in Australia, the most important one was installed in 68, 69, and it looked at 77 different timber species. It was sort of the Rolls Royce of how to set up a natural durability trial. That was conducted in 5 different test sites through Australia. There were 10 replicates of each timber at each site, and 2 of those came from different trees, so there were 5 different trees, and those trees were also sourced from fairly wide locations where the timber species grew. And they all came from the butt log, and the last inspection I looked at that after, and that was after more than 30 years when the final inspection was done on that one. And that's how the test looks before and after installation. That's the site at Sydney. And the stakes were inspected by pulling them out of the ground, probing with a knife to determine depth of and extent of decay and termite attack. And they were given a rating, a CSIRO rating system that we used from 8, which is sound, to 0, fully destroyed, and there's some example stakes of the 7 to 2 ratings. So that trial gave the relative order of durability of all those timber species, and in the trial was also for comparison CCA treated pine sapwood and also creosote treated pine sapwood. And the trials showed that those treated pines were actually more durable than all of the naturally durable timbers. But the other thing to consider with timber treatment is that while with radiata pine, while the sapwood is very easy to treat, the heartwood is difficult to treat and usually doesn't treat properly. And also if the timber hasn't been seasoned properly, so there are still damp, wet patches within the timber, you might get poorer penetration of preservative then as well. So these are examples just before I came from my own backyard. So a CCA treated pine post after 4 years, a lot of brown rot in there, whereas the eucalypt post was already an aged railway sleeper, and then it was in ground as a post for more than 20 years, and it's still doing pretty well, doing pretty good. So there's certainly a role for natural durability. Probably the best combination would be naturally durable timber coupled with treated sapwood. But of course, one of the benefits of natural durability is the non-toxic or the environmental credentials that come with it. So I'll just go through some of the various organisms that can attack eucalypts. So the first one there is the Lichtes beetle or powder post beetle. These are quite widespread, so they'd be here as well in New Zealand. A lot of, probably most eucalypts would have susceptible sapwood, so it's an important thing to treat against. There are some timbers that are naturally durable or naturally resistant to Lichtes, and they would have low sapwood low starch content in the sapwood, or the vessels, because the beetle lays its eggs in the pores or vessels of the eucalypts, and if those vessels are too small diameter, they can't lay their eggs in there, which makes the timber immune. They're probably more, Lichtes is probably more of a problem, although they're fairly easy to control with preservatives, but more of a problem for eucalypts than anobium is for radiata pine. So if the timber was being used indoors, you could treat with boron preservative, a leachable preservative, but it's very effective and quite a safe preservative. Or if it's used outside, you would use one of the copper-based preservatives or a light organic solvent preservative. Not so much importance in New Zealand, although we do occasionally send some termites, coptotermes, over here in power poles or recycled poles used for landscaping and such like. But this shows how termite resistance could be determined in Australia. So the test specimens are placed with bait wood in the metal drum, and it's all enclosed, and the connection to the mound is covered over with soil. So you could do that with coptotermes, the two main species of coptotermes and mastotermes in Australia. Some recent trial that we did shows that when we say termite resistance, we're actually mainly meaning resistance to coptotermes, which is a species that occurs throughout mainland Australia. So you see the mass losses there. There's still some mass loss there, 12% or 11%, but compared to mastotermes, the giant northern termite, it's even termite-resistant timbers aren't being controlled there. And that's a termite that only lives in tropical Australia. But I think what's happening there as well is that if all of that timber, all of the timber in that drum had been the one kind of naturally resistant timber, then the termites might not have attacked it. So if all of your house frame was red ironbark, I think it would probably be resistant, whereas if you put untreated wood or bait wood virtually along beside it, well then that termite species can attack the timber. And then there's Marinebora trials to determine those durabilities. They were determined, some of them with aquaria trials, some with small specimen tests that were hung at 3 different test sites in the sea. And then there were also trials or experience from just known performances of timber marine piles. I'll just move now on to one of the projects that we did, looking at natural durability of timber, how it varies with tree age. So we looked at 3 ages, less than 25 years, trees 30 to 50 years, and then mature 80+ year-old trees. Also yardstick timbers were included there to get an idea of durability, and it was an above ground trial, and there were 10 replicate panels and 1 replicate from each of 10 trees. And on the right there, you see some of the panels turned upside down, so you can see some of the brown rock decay in that case at the bottom end, or where the nail is. So the flat panel test has a bottom sort of L-shaped lip of non-durable timber, and that becomes a water trap. The test panel sits within that, and that's where decay usually starts. For spotted gum, the spotted gum eucalypt, even though it's Corymbia, but still call it a eucalypt, there was quite a nice trend of tree age versus durability. So these were inspected after 9 years, so it's quite good long-term results. There wasn't much difference in durability between the 30 to 50 and mature trees, which was quite a good result. And there was also a nice trend for the young trees where as they became more dense, they became more durable. It was a fairly similar result for red ironbark, although not quite as clear, but not as nice a curve. But you can see that the younger trees, or the diamonds there, they're all less durable than the older trees. Whereas when we came to sugar gum, there wasn't much difference really between no matter what the tree age was. We thought that the reason for these differences is the actual exact age of the young trees. So this next slide looks at that in a bit more detail. So the 30 to 50 and the 80+ year trees, you can see the densities there are fairly similar between them, where comparisons are available, and the decay resistance is also fairly similar. Whereas the less than 25 year trees, I've included in there the mean age of those actual trees. So the younger trees, 15.6 years, had lower density and also lower decay resistance. Whereas when you get to sugar gum, which is the species where we couldn't really find much difference between the different age groups, they were actually the oldest trees in that set at 24 years of age. So there seems to be something important happening in regards to durability in the 15 to 25 year period. And we know that a lot of the eucalypts don't start producing mature heartwood until their trees are 9 to 13 years of age. And then, of course, you need some years for it to actually get some volume, wood volume there that can be used for testing or use. In another project that we did was looking at eucalypt thinnings for vineyard posts. So this shows a CCA radiata pine post that was included in that trial, and after 5 years in an actual vineyard, it broke, as did a number of other CCA posts. They broke during harvesting. So there's some examples of the plantations where the thinnings were taken for the trial, so sugar gum and blue gum, those examples. All these posts were then preservative treated either with what's called ACQ preservative, which is a copper-based preservative, an alternative to CCA because it lacks chromium and arsenic. Or the other treatment was with creosote. Well, I don't think you do use creosote in New Zealand, but there's several treatment plants in Australia that do treat with creosote. After the timbers were cut into posts, they were all seasoned under hessian, just air dried. Anything harsher and they'd probably split. Some of the posts were also gang nailed on the ends, and some were dried while the bark was still on, although I wouldn't recommend that. We got quite a bit of borer damage under the bark on those seasoned with bark on. The drying with gang nails on the end had a small, or gave some improvement, so those averages there are for all the hardwood timbers across all species. So there was a small reduction in splitting for creosote treated posts from 26 to 12%, and for ACQ a small reduction as well. And the creosote treatment reduced splitting compared to ACQ treatment as well. But it was probably best really to look for those timber species that are naturally just don't split anyway. That would have been the better way to go. So a selection of those posts in that trial were then strength tested by some collaborators near Mildura, and the strengths the mean bending strengths that are attained for the ACQ treated posts. You can see that all the eucalypts were stronger than radiata pine posts. In this trial, the ACQ treated radiata pine, the second column there, was actually a bit weaker than CCA treated pine, but that's not necessarily a consistent finding for ACQ treated timber, but it was in this case. Another important thing to look at for vineyard posts is degree of splitting. The splitting probably doesn't reduce the strength that much, but it does make it, if the split's in the wrong location, it's difficult to put a staple in to hold the wire for the vineyard, and also the deep split can also accelerate decay within the heartwood internally. And on the right there, you can see some of the longicorn beetle borer damage for that post, which had been seasoned with the bark on. Whereas if we looked at the timbers were spotted gum, rose gum or grandis, and also sugar gum. They were the best species in terms of not very little splitting for those species. So we thought for those timbers they would make good posts. It's interesting that the grandis was so good in terms of not splitting, whereas the sort of anecdotal evidence, well, I've heard from some treaters that grandis, when you're getting to pole-sized timbers, that they do suffer too much from splitting, which is the main reason they're not often treated as poles. So just tree age, that property can change. So if you're growing trees for vineyard posts, it's you need to remember that a post of that diameter, that most of the heartwood that you'll have in there will be what sort of becomes the inner heartwood, so it won't be as durable as the outer heartwood. So the alternative there is to treat there'll be some durability there if it's a naturally durable species, but you still need to treat the sapwood to give good protection, or grow the tree to a larger size, older age, so that you've got more outer heartwood in there that you can then saw off the sapwood if you're not wanting to treat. For determining natural durability, you could do fungal lab trials, and that's an example of one of the trials. They can be done in shorter time, or there's a lot of variations could be done there. So that's one method, and that's just an example of a recent trial where I did one of these, and these blocks had been artificially weathered beforehand, and there's enough mass loss in there where you could look at variations to get some results. It's not much use if all the timbers that you expose all have less than 3% mass loss, for example. It won't tell you much. Another way to look at durability is as in-ground stake tiles, or in soil beds within an incubation room. And that's all. Thank you.